What's up, everybody? Today we're going to check out the mathematics behind the rule of 72, which is a rule that's used in personal finance. So first off, if you're not familiar with this rule, it basically says that if you take 72 and divide it by your interest rate or your return rate on an investment, it will give you approximately the doubling time in years. That is the time it'll take your investment to double. So a quick example of this is, let's say for example you have a 6% return on an investment. You could take 72 divided by 6, or really what we're doing is we're going to take 0.72 divided by 0.06. Kind of get into this in a minute. These are both the same number, but this comes out to be 12, and that tells you that it would take you approximately 12 years to double an investment that was getting a 6% annual return. We could double check this really easily by just going into our compound return formula, which says that the total return is equal to the principal, which is the p-value here, times 1 plus the interest rate or the return rate, all raised to the number of years. So in this case, we could say, let's pretend that we invested $1,000 at 6% return. This rule up here told us that we should be able to double our money in approximately 12 years. Let's see what that is. I can check out the calculation here. So take $1,000, 6% return for about 12 years. Yeah, you can see it's pretty close to doubling. We're going to get about $2,012.20. So again, it's just an approximation, so it's not going to be exact, but it's a nice way to do these approximations really quickly in your head. Just to kind of another quick example, if you took like a 10% return, you would expect that to double. Again, I'm going to do the 0.72 over 0.10. It's really the same as 72 over 10. This is actually the one you're probably going to do in your head. But this tells you that in approximately 7.2 years, your investment would double. And obviously this is really important because the shorter amount of time it takes for your investment to double, the more money you'll have over a certain period of time. All right, great. So that's what the rule of 72 is, and you probably already know that if you're watching this video because you're trying to figure out where this actually comes from. So let's actually take a look at how we can show that this works mathematically and where this approximation actually is created. So again, I'm going to start with my compound return formula, and for my final value, I'm just going to make this double the principal. So whatever the principal it is, we're going to make it twice that much because we're trying to double here. If you wanted to, you could put in like $100 here and $200 here. It doesn't really matter, because really all we're going to be doing is dividing out the principal, and that's going to always leave us with a 2 on the left hand side. So we'll always end up with an expression that looks something like this. So what we're trying to do is we're trying to solve for the t up here at the top. We're trying to solve for the amount of time it's going to take for this to double. In this case, t represents the number of years, r represents the interest rate. And if you remember from your high school algebra, or maybe college algebra, the way that we can get a exponent down out of the exponent is that we can take the logarithm of both sides. In this case, I'm going to take the natural log. We could take whatever log we want though, but you'll see with the natural log why this is really beneficial for the rule of 72. And then our algebra rules state that once we take the log, you can drop this exponent down. Now, fair warning, we're going to get into a little bit of algebra here, so hopefully it's not too scary. But yeah, we're going to get a little nerdy here with some of the math. All right, so now we're going to have natural log of 2 is equal to 2 times the natural log of 1 plus r. If we want to solve this for the time, we just need to divide by this right here, the natural log of 1 plus r, and we'll get that the amount of time to double is natural log of 2 over natural log of 1 plus r. Now, an important thing to note here is that this is the exact doubling time. So we said that the rule of 72 was an approximation. You can use this formula to figure out the exact amount of time it would take an investment to double given a particular annualized return. So for example, let's go back to our 6% return situation. If I wanted to figure out the exact doubling time, I could put in 6% for the R. And if I drop that over here in my formula, let's do natural log of 2 divided by the natural log of 1.06. You'll see that's about 11.89, about 11.9. If you remember earlier, we said the approximation for this was about 12 years. So 11.9 is the actual. Again, that's a slight rounding, but 11.89566, that's like the exact number of years it would take it to double. So this is actually a really convenient formula to kind of know if you want to do an exact value and you got a calculator or a phone or something on you, you can just throw that in really easily and do the exact value. Another cool thing about this formula is that you can use it for basically any multiple. So if instead of doubling, if you wanted to triple your value and see how long that would take to triple your money, you could just replace that 2 with a 3, and then you could use the exact same formula. Or if you want to quadruple, put in a 4, etc., etc. All right, so that's cool, but that doesn't really tell us why this formula approximates with the rule of 72. So to figure that out, let's actually break this down a little bit. All right, so I'm going to take a look at the natural log of 2 here with my calculator. So you see the natural log of 2 is about 0.693147. So I could say technically that, I could use like 0.69 up here. The problem is that 69 doesn't have a lot of factors. It's really only divisible by 3 and I guess 23. So it doesn't really help you with a lot of different interest rates. So what we're going to do instead is we're going to actually use 0.72. And that's because 72 is divisible by a lot of numbers: 2, 3, 4, 6, 8, 9, 12. So it's really easy to use with a lot of different interest rates. So that'll be kind of our first approximation. Natural log of 2 is really close to 0.72. And then you might say, well, that's great, but the rule of 72 says that you should take 0.72 divided by just the rate. But over here we have the natural log of 1 plus the rate. So how do we get from there to just this R value? Well, for that we need to take a look at the natural log graph. So if you remember from high school, we could graph these logarithmic functions. All right, so let's take a look at the natural log graph. It looks something like this. The natural log of 1 is equal to 0. But then if you look at adding 1 to the inside of the natural log, for example, if we were looking at 0.02, for example, this would be like having the R set at 0.02. And that's like kind of like having 2%. And if you notice here, R is equal to 0.02, the output is really close to 0.02. So this is 1 plus 0.02, and the natural log of that is really close to just 0.02. And this is true for most of the values that are small. Like if you look at 1.04, you'll get an output that's really close to 0.04. And same thing, like 0.06 is really close to an output of 0.06. And this just has to do with the nature of the logarithm function, that it looks very similar to a linear function here for these early values before it starts to curve to the right. Now you will notice that this doesn't always hold true. It does start to deviate away, like here at 1.2, instead of being at 0.2, it's closer to like 0.8. I'm sorry, it's closer to 0.18. So we got to be careful there that this doesn't always approximate these values. But for these small values, whenever R is really small, the natural log of 1 plus R is really close to just R. And that right there is where the rule of 72, comes from, or at least why it works. So that's kind of a cool feature of it, and it just has to do with the fact that those natural logs are really close at those smaller values. Now, like I said, we do have to be kind of careful, and this is kind of some bonus material here to go a little farther down the rabbit hole, that the rule of 72 actually doesn't always give a super accurate value. I mean, it's pretty good for most values, but it's better for some rates than others. So one thing we can do is we can actually look at the exact value versus the approximation that the rule of 72 gives me. So if you remember, the exact value we got was the natural log of 2 over the natural log of 1 plus the interest rate. Okay, and then the rule of 72 says that we want to take 0.72 divided by the interest rate. So what I'm going to do is I'm just going to look at some different values of R. We'll go from like 0% up to 200%. I want to go with a step of 1% for each of these. And you'll notice that when I get down here in these values that we're kind of usually talking about with like index fund, mutual fund returns, if we're hanging out around like 6%, the difference is pretty small. This is like 12 years to double versus 11.9 years to double, so it's not too far off. That's the one we were looking at earlier. If we go up to like 8%, it's super close. So the difference between 8%, I mean, that one's like almost dead on. The approximation says 9 years, and then the actual value says about 9.01 years. So it's within 6/1000ths. Interestingly, if we go down to like smaller percentages, these actually start getting off by a bit more. So like if you look at 2% return here, the approximation says 36 years, but the actual value is about 35 years. So it actually is a little bit shorter than we would get from the approximation. If we go down to 1%, the value is off by about 2.5 years. So maybe not significant, but at least in your mind. But once you start doing calculations with things that are off by a decent amount, if you do the calculation over a long period of time, it could potentially cause differences in your calculation. The other thing that happens is as the interest rates start getting bigger, or the return rates get bigger, you'll start to also see a separation. So they get really close together around like 8%, 9%, and then as we get higher, you'll start to see that these values separate a bit. And we're getting, we're actually, the rule of 72 gives us a smaller estimate. The estimate is actually a smaller doubling time versus the actual doubling time up here, which could potentially get you in some trouble if you're running a calculation for a long period of time. And then even if we get above like 100% return, you'll start to see where the differences start to get a little bit bigger as well. Now, if you want to get super mathy about this and kind of super nerdy, we can also take a look at the function that would be the function of the difference between these two values. So I can actually graph it like this. Let's look at a function that shows the difference between the actual doubling time and the estimate for the doubling time. So this is going to be the green line here. And again, what we're looking at here is the x value, or the horizontal value, that's the return rate. And then the y value, or the vertical value, that's the difference in the estimate with the rule of 72 and the actual amount of time it takes to double. So you see, as the interest rate gets really low, like 1%, 2%, the difference is actually pretty large. This is where you see like the couple of years difference, right? At like 1%, there was like a couple of year difference. I think it was like a 2.5 year difference. And that's where the actual value is a little bit smaller than the approximation, and that's why we're getting negative numbers here. And then as the interest rate starts to go up and get closer to like 5, 6, 7%, you'll see the difference. Like here's Here's 6%. The difference is only about 1/10 of a year between the approximation and the actual value, so that's pretty good. And then remember, when we looked at 8%, that one was really close. So there's almost no difference at 8%. It's off by less than a hundredth of the year. Those are almost the same values. And then you'll see as the interest rates or the return rates get bigger, the difference between the approximation and the actual value start to go up. But they do start to, the rate of change starts to go down, which means that the difference doesn't grow as fast. So the difference grows pretty quickly here, and then once we get up here, the difference doesn't grow so fast anymore. And that's kind of what was happening whenever we were looking at, like this rate. Let's do a little calculation here. This rate minus this rate. As you move the R, you can see like the difference down here is pretty small. This is the difference between the approximation. We're looking at this number right here. So when the interest rates are like, this was the 8%, the difference was very minute. And then as we start going up, you'll see that the interest rate, the difference starts to go up. And then there's a certain point though, where it actually starts to come back down, which I thought was pretty interesting. So the difference is actually coming down here. And actually, if I expand this to get to like really high returns, like a 300% return, for example, you'll see that the interest rate actually, or the difference actually starts to come down, like the difference between the approximation and the exact value. So you can actually see that with the graph as well. If we look at this this green graph, you'll see that it actually goes up for a while, and then it hits a certain inflection point. I'm not sure exactly where it is. We'd have to do a little calculus to figure out exactly where it is. But then it actually starts to come down, so the difference actually starts to, the values actually start to get closer as the interest rates as the return rates get really high, which I thought was kind of fascinating. If you're getting really high return rates here, you're probably not too worried about the rule of 72. But, it's just kind of an interesting mathematical phenomenon to look at. All right, so some extra super bonus, super nerdy mathematics material. So let's say that you were trying to show the rule of 72 even more accurately. What you could have done is, when we were at this step, what you could have done is, instead of using the natural log, is you could have figured out what log base could I have taken of 2 to actually get exactly 0.72. And to do this, what you'd have to do is rewrite the log rule into the exponential form. Again, getting super nerdy here, super mathy. And we could actually figure out what that base needed to be. So what I could do is rewrite this 0.72 as 72 over 100. And then to figure out what the b is, I could just take both sides as the power of 100 over 72. And this is going to give me the exact log base that I would need in order to make that equal 0.72. So again, I'm just trying to show you like kind of an even more accurate way of proving the rule of 72, or showing at least why it works. So I could do this calculation and use that log base. So log base of, let's see, 2.6, let's go 2.6188. So I could have taken that log base of both sides whenever I was trying to solve this equation up here. And if I do that, I'll end up with something like this. And now if I bring down the t and then divide by all of this, I'll get, this kind of uglier equation, but it'll be a little easier to actually show that the rule of 72 works. We already said that this number on the top is, should be equal to 0.72, or at least we rounded a little bit, so now it's an approximation. All right, and what will happen now is that if you use this log base that I have here, so that's 2.6188. If I use this for like 1 plus 0.05, I'll actually get an even better approximation for the rate. So this is again 1 plus R, and you see this is really close to R. It's really close to the 5% rate. It's actually closer than if we used the natural log. Remember we said the natural log was pretty close, but that one is actually super close. So we could show this with, you know, a bunch of different values, you know, like 10%, 10% here. You know, see, those are really close. I mean, you'll still have the same situation where if you were to use this, you know, graph it as a function, we're still going to get to where it's going to start varying a little bit from the linear path. You know, it's really only good, you know, up to certain interest rates. You know, you start to see some variation at like 20% here, and you know, a little bit farther on. Let me build this out a little bit. You start to see variation versus, you know, this is 1.3 to 0.3. That's what the red line represents, and then the black line is the logarithmic function. But you know, this is still a really good approximation. So we could go over here and say that, like, you know, this again for like really small values, this is even a better approximation for R than we had with the natural log. So again, if you're looking for like a even deeper rabbit hole to go down to show where the rule of 72 comes from, you can use this different log base and go from there. But the same thing, and you know, we still have to be careful of, you know, when we're using it, it's not always super accurate. There's certain interest rates that it's better for than others. So hopefully that's interesting, and if we're looking for some kind of explanation as to why this rule works, hopefully that gives you a little bit of insight.